this video, we're going to look at vertical and horizontal asymptotes. Just a bit of a review. An asymptote, we'll remember, is a line that a graph approaches as it heads towards either infinity vertically or horizontally. Just to briefly mention, I have the phrase or curve here. Asymptotes can be curved, and a graph can approach a curved shape as it goes towards infinity. However, typically the word asymptote is restricted to linear asymptotes, and in our context, we're going to restrict to linear asymptotes as well. We have three types of linear asymptotes. We have vertical, we have horizontal, and we have what is known as either slant or oblique asymptotes. We're going to, in this video, primarily deal with the first two, and we're going to reserve oblique for a little bit later. There are different ways to approach calculating vertical and horizontal asymptotes. A vertical asymptote is formed by a restriction to the domain. And so that's what we're going to look for when we want to find out where those vertical asymptotes are. While as horizontal asymptotes are based upon the limits of a function as x approaches infinity or as x approaches negative infinity. We're primarily going to work with rational functions, and in the case of rational functions, these two limits are going to equal the same thing, but you can find some functions where the horizontal asymptote to infinity is different than the one to negative infinity. So let's start with vertical asymptotes. If we want to find the domain restriction for our f of x function, we need to know when the denominator is equal to 0, and that's going to happen at the value x equals 2. And so that means when we were to graph this function, we would find a vertical asymptote at x equals 2. The graph can never have an output at this input because the function is undefined there. For g of x, we're going to do the same thing, but figuring out when this denominator is equal to 0 is going to require some factoring. And so once we factor, we'll find that x can equal 0 or x can equal 2. So this graph will have two vertical asymptotes. And for the third one, the same process. And we'll find once we factor that x can either equal negative 2 or x can equal 2. However, h of x in fact only has one vertical asymptote, and let's see if we can figure out why. If we take the numerator and factor it, we're going to get x plus 4 times x minus 2. And our denominator, when factored, we didn't actually factor it, x plus 2, x minus 2. We're going to find this factor of x minus 2 occurs both in the denominator and in the numerator. And whenever this happens, we have what is referred to as a removable discontinuity. Or we would just say there's a hole in the graph there. So we're not going to find a vertical asymptote. The graph doesn't approach this vertical line as it goes to infinity in the y direction. Instead, we just find a hole. So our only asymptote is x is equal to 2. So our process here is finding out when the denominator is equal to 0, being careful to remove any holes from the graph before we calculate those vertical asymptotes. Let's turn our attention to horizontal asymptotes. And as we said, horizontal asymptotes are based upon limits. And so we want to know the limit as x approaches infinity of our rational function. In this case, x cubed minus 1 over 2x plus 1. And we'll remember that all we care about are the highest degrees of our two different polynomials. In this case, the numerator has a degree that is greater than the denominator, and that tells us that this limit does not exist. And since this limit does not exist because it goes off to infinity, there will be no horizontal asymptote. Moving on to the second one, we see a problem where the exponent in the denominator is larger than the leading exponent in the numerator. And in this case, the denominator is going to grow significantly faster than the numerator. So our limit of g of x in this case is going to equal 0. And so we'll see that there's a horizontal asymptote at y equals 0. And this is the value that the graph will approach as it goes towards infinity. And because this is a rational function, as x goes to a negative infinity as well. In the last problem, we have exponents that are the same in the numerator and denominator. And so we will hopefully remember that in this case, our limit as x goes to infinity is going to be equal to the ratio of the coefficients of those two leading terms, or in this case, 1/2. And so we're going to find that y is equal to 1/2 is going to be a horizontal asymptote here. And so you're going to want to pay attention to what those limits are and remember our rules about comparing the exponents of the leading terms of polynomials in the numerator and denominator in order to calculate the horizontal asymptote if one exists. One final distinction between horizontal, oblique, and vertical asymptotes, and that is that a vertical asymptote, which we can see in the second graph, I didn't draw them, but they are there. Vertical asymptotes can never be crossed by the graph, and that's because they're created by restrictions to the domain of the graph. That graph, or that function, is not defined at that x value, and so you will never have any x coordinate that gives you an output that's on that vertical asymptote. However, that is not true of horizontal and oblique asymptotes. You can have functions that cross over those types of asymptotes, and I've given you 3 examples here. Here we have an asymptote that is y equals 0, but the graph crosses it at the point -2, 0. And it's just then that once it goes below the x-axis, it then approaches the x-axis from the negative side as we go towards negative infinity. In the middle graph, we actually see an asymptote that is crossed twice by the graph. Okay, but we're still going to have behavior on both the left and right side of the graph, where as the graph goes to infinity, it is going to approach that oblique asymptote, the same as we go towards negative infinity. And the final example is an example of an oscillation. Sometimes you can have a graph that oscillates to either side of a horizontal asymptote, but you can see that the amplitude of these sine waves is getting less and less and less and less as we go towards infinity, and the same towards negative infinity, because this graph is approaching 1 as you go off to either the right or the left.